All set to go? Fine? Good afternoon, everyone. It's a great pleasure that we have a distinguished scientist, Professor Dr. RAVI, who hails from Shimoga, Karnataka. And then he, during the process of the finding the career, he moved to United States after doing MSc in Mysore University, and partly he was a student at IIT also for some time, and then he moved to University of Florida where he did his doctoral work, and then he was a postdoctoral associate in the University of Maryland, and then he was an assistant professor at Georgia Tech, and he moved to National Oceanic and Atmospheric Administration, Boulder, Colorado, where I was associated with him as a postdoctoral researcher after my PhD from Indian Institute of Science. Dr. Ravi Shankara is a university distinguished professor in the Department of Chemistry and Atmospheric Science at Colorado State University. Previously, he was at National Oceanic and Atmospheric Administration as the director of the Chemical Sciences Division, formerly Aeronomy Laboratory, at NOAA's Earth Systems Laboratories in Boulder. Over the past 4 decades, he has worked on the chemistry of the Earth's atmosphere related to stratospheric ozone depletion, climate change, and air quality. His laboratory and Earth's atmospheric measurements have contributed to deciphering the ozone layer depletion, including the ozone hole, quantifying the role of chemically active species on climate, and advancing understanding of the air pollutants formation, removal, and properties. Dr. Ravi Shankara is a member of the United States National Academy of Sciences, a foreign member of the Royal Society, London, and a foreign fellow of the Indian National Science Academy. He is also a fellow of the American Geophysical Union, the Royal Society of Chemistry, the American Association for the Advancement of Sciences, and the International Union of Pure and Applied Chemistry. His many awards and recognitions include an honorary doctoral degree from the University of York in the United Kingdom, the Montreal Protocol Scientific Leadership Award, the Polanyi Medal of Royal Society of Chemistry, the Stratospheric Ozone Protection Award of the United States Environmental Protection Agency, the Silver Medal of the United States Department of Commerce, National Academy of Sciences Robertson Memorial Lecture and Medal, and the American Chemical Society's Award for the Creative Advances in Environmental Sciences. He has presented numerous named lectures in many countries. He was the chair of the board on the Atmospheric Sciences and Climate of the National Academy of Sciences from 2014 to 2021, and co-chair of the WMO UNEP Science Assessment Panel on Stratospheric Ozone from 2008 through 2015. He is a member of the Science Academy panel of the Climate Clean Air Coalition of UNEP and the advisory committee for the Vienna Convention Trust Fund. He is on the editorial boards of the Proceedings of National Academy of Sciences, which in short we call PNAS, and other journals. He has previously served on many other editorial boards and was the editor of Geophysical Research Letters. He was a co-chair of the Air Quality Research Subcommittee and Interfederal Agencies Committee before leaving NOAA in 2014 as the director of CSD. He is an author or co-authored of more than 400 peer-reviewed publications, including Science, Nature, and many other reputed journals, and scores of data evaluation and assessment reports. In addition to this, he is currently Infosys Distinguished Professor at the Indian Institute of Science, Bangalore, and he has been in many committees of IPCC and other assessments, JPL evaluation data. In addition, he was also advisory, he was in advisory boards of many in Government of India, particularly Ministry of Earth Sciences. With this small introduction, what I know, I am very privileged to work with him as a postdoctoral associate. Ravi, we welcome you to the department. Sanjay, to please welcome him, and please go ahead with your lecture. Thank you. Thank you very much. Thank you. Yeah, fine. Okay.
Can you all hear me? Can they hear me?
Yeah, they can hear.
Okay. Thank you for the opportunity to talk to you about a few things. I realize that many of you are not atmospheric scientists, and I apologize to those of you who are, because I'm going to kind of use words in simple ways, simple words, to explain certain things. Okay. So I just want to assure you there's actually science behind all this. So if you want to, we can talk about it afterwards. So what I want to start, what I'm going to tell you about is going to discuss what is the contribution of the regions of the world to climate change to date and to in the future, and but including not just greenhouse gases, but also aerosols. Aerosols are these very tiny particles that are suspended in air, and they actually have a significant effect on climate. And as you probably know, they have even more of an influence on air quality. The biggest problem, for example, air quality in India is particulate matter. Okay? So I'm going to just very briefly mention how we use satellite data to derive surface PM 2.5. PM 2.5 is particulate matter of diameter less than 2.5 micrometers. Okay. And then the health impact of those PM 2.5. Can you hear me now? Okay. And then it's one thing to talk about what the problem is, but what can we do about it? So one of the things I'm going to show you is some information we got from looking at what happened during COVID shutdown to get an idea of what kind of reduction you would need. Okay. You know, COVID was all bad because there's a silver lining to all this, right? Don't let any disaster go to waste. Learn something from it. Then I'll just tell you my thoughts on what we need to know better, need more, and a very short summary. So that's what I'm going to try to do. So for those of you who already know, greenhouse gases warm the planet. Okay. If you could see it, that red arrow is the positive arrow that can warm. Okay. And then aerosols, on the other hand, which the blue arrows, that cool the planet overall. So the combination of the two is what really matters. That's clear, right? You can't just ignore it. So the other way of looking at it is the aerosols today have actually masked the full impact of greenhouse gases. If they weren't there, it would have been much worse. Okay? So, greenhouse gases, as you know, mostly what we worry about is the human-induced greenhouse gases. But in addition, the same or very similar human activities are also affecting aerosols. Okay. So, let's look at the differences between greenhouse gases and particulate matter. The first thing about greenhouse gases is they're very long-lived. They live in the atmosphere. Once you put it in the atmosphere, most of them live for a very long time. In fact, if they don't live for a very long time, they are not very good greenhouse gases. Okay. They have to accumulate in the atmosphere. So things like CO2 has a lifetime. It doesn't have a simple lifetime, but if you were to look at it, it's about 100 plus years. N2O has a lifetime of about 110 years. Methane has a lifetime of about 10 years. CFCs have lifetimes of 50 to 100 years, and some of them even more. And so that's the long-lived. On the other hand, aerosols are very short-lived. you know it's so. Okay? Is it really bad outside today? If it rained yesterday and rained today, would it be hazy? It's removed very quickly. Usually these pollutants live for only about a week to 2 weeks. So the fact that they do not live in the atmosphere means they don't accumulate in the atmosphere. I'll show you an analogy in a minute. The greenhouse gases absorb the infrared radiation, so it prevents what could have been out from going out. Aerosols, on the other hand, prevent the visible radiation from coming in. Okay? So that's another big difference. And the most important thing is the direct health effects of greenhouse gases are pretty negligible. You know you can breathe CO2. Right? You actually make CO2 when you breathe out. Anybody know how much CO2 you breathe out when you get out? It's actually a lot more than what's in the atmosphere. And on the other hand, aerosols or PM really affect your health. Okay, so I'll be talking only about the direct health effects. So now you might ask yourself, what are the indirect health effects? How do you actually measure health effects? So I'm going to use a metric called premature mortality. So what are the chances that somebody is dying because of exposure to that? But there are other major impacts. You could have asthma. You can't go to work. You have to go to see a doctor, all sorts of stuff. That's not included in my calculation. So we always hear about who emitted what, who's doing what. So the question that comes up is, which countries have emitted greenhouse gases and all of these things? It's not a question of blaming them per se. It's a way of saying, what is the legacy towards? So you can do it country by country, but what happens is that because of the information we have, it gets very noisy. And also, if you think about it, countries in certain regions develop kind of together, roughly. So Indian subcontinent develops in one way, the Western Europe develops another way. To make the life easier, I'm going to clump them into regions, which I'll show you. So then we calculate what is the effect of not only the greenhouse gases they emitted, but also the aerosols they emitted. Okay? Don't want to go. Okay. Now, as I mentioned, on the left-hand side, it's really, I'm sorry, all these things are very distorted, and you can't see the colors. This is roughly the current emissions of greenhouse gases as a pie chart. As you can see, we always think of China is a huge emitter. India is a smaller sliver, but North America is a big sliver. Okay? But that's what's happening today. But what we really want to know is what has happened over the time. So what you look at here, down here, is essentially just the effect of greenhouse gases, and even the CO2 emitted in 1900 is still here. So as you keep emitting it, it accumulates and it contributes more of what is called the radiative forcing. For those of you who may not know radiative forcing, I'll show you, I can explain it to you after the seminar. So North America clearly is a very big contributor. Then look at all these other countries, and this is China, this is India. You can't see the colors, I'm really sorry. Okay. But if I account for not only the greenhouse gases that were emitted, but also the aerosols, this is what it looks like. Until about 1960, the contributions were very small overall, 1970. And then, as you can see, North America just kind of was shooting up. Okay? And then there was the Western Europe, and China is just breaking out. India is still not breaking out. So what that means is even though we are emitting greenhouse gases in India, because we have so much pollution, we haven't contributed so far to the climate change. Okay. On the other hand, if you look at the other ones, they have committed a lot more. Now, you might want to ask yourself, why do I want to know this? I would argue that you need to know it because it's not a question of what you're going to do now, it's a question of what you have done in the past. If I were to use a very bad joke, karma is going to catch up with you. Okay, so you can do it in a quantitative way, and the way you think about it is think of this as the balance in your account. Okay? So you can put some money in multiple sources, or you can be taking something out, okay, not putting it in. So, but there is something that's always going up. That's called, because the earth always radiates out. So it's just directly proportional to, Stefan Boltzmann constant, the earth, and sigma t to the 4. And it's called actually net flux imbalance. So if you add more of this and don't take out as much, it will rise. But on the other hand, if you just keep taking it out, it will be lower. So it will reach kind of a steady state, but not quite. Okay. So this radiative forcing, three things I'm showing here are this is the greenhouse gases, this is the aerosols, this is land cover and land use change. That's also another major contributor. And then this is the constant amount that's going out because of the earth is radiating all the time. So if I look at the global radiative forcing based on the emissions, this is what it looks like. But what you really want is how much we have accumulated. And that essentially is the area under the curve. You integrate the curve. Okay. So radiative forcing is watts per meter square. And if you integrate under the curve, what do you get? You get the total amount of joules. That's really what you want to know. So we can do that very simply. And essentially, that's the equation for you. It is the net radiative forcing for all of the different components, and you integrate between T1 and T2 depending on what you choose for T1 and T2. So what I'm going to choose for T1 and T2 is 1900 to about 2017. Okay? Now the reason those are the dates is before 1900, even though there was industrialization, it was not on the same scale. It was pretty small. But I didn't do beyond 2017 because when we first started the calculation, that was 6 years ago. Okay. Now, once I do that, incidentally, I want to tell you there's actually real equations behind this, and you can look at it. It's essentially, there's a linearized climate equation, and net imbalance N is equal to radiative forcing minus lambda delta T, and you can get these quantities. And we define something called a cumulative radiative force. That's the area under the curve. Okay. So let's look at those. This is a little bit of a complicated slide. So let me just kind of very quickly go over this. First of all, I want to define a unit for you. It's called yotta-joules. That's 10 to the 24 joules. Okay. You're all chemists. Think of it as a mole of joule, roughly. Okay. Now, if you look at the total cumulative radiative forcing for the Earth from 1907 to 2020, it is 3 yotta-joules. So let's compare it with the total energy from the sun that's received at the Earth's surface each year is about 2.5 yotta-joules. In other words, we have absorbed only 1% over 100 years. I mean, one equivalent of 1 year in 100 years. Okay? And just so you can put that in context, total electrical energy we consume is about 0.02% of the sun's input. So there's a lot of room to do, collect and use solar energy. Okay, then if you look at this, the contributions, this black bar is the contribution of the net greenhouse gas and aerosols by North America. This one is from Western Europe. This is from Russia and Eastern Europe. This is China. This is the Indian subcontinent, which includes India, Pakistan, Bangladesh, Sri Lanka. I think it also includes Afghanistan. And this is other Asian countries, Middle East, Latin America, and the Pacific. Okay? So you notice that in this figure, North America has contributed about 3 times as much as China and India. As you notice, China has contributed less than India, amazingly. The reason is it was even more polluted in China until they started cleaning up. Okay? Then you ask yourself the question, incidentally, these bars are when you include land use and land cover changes. Suppose I stopped emitting everything today. What will be the contribution in 2100? 2100 might seem like a long time for you, but when my granddaughter was born, I was holding her one day. She was born in 2015, and it occurred to me that she's going to be alive most likely in 2100. So it's actually a date that means something to me, even though I'm going to be dead for a long time. My granddaughter is very likely going to be there. And she definitely will be only 35 years old in 2050. And you're all going to be there, folks. So just think about it. So if you do that, even if you were to completely stop emitting today, by 2100 the contribution is so large in North America. The reason is twofold. If you stop emitting everything, the aerosols go away and the CO2 stays there. Greenhouse gases stay. Okay? And you can do the same thing for other countries. And also there are some very interesting points here I don't have time to. For example, Western Europe, including land cover and land use, makes no difference because Western Europe deforested a long time ago. Okay? And you can see all sorts of interesting stuff there. So you get the idea. Okay? So the people with the largest legacy is right here. Now, let's kind of put this in context. And this is a much simpler diagram. What it shows on the top part here is contribution. This is somewhat of a different units from what's called OECD countries. OECD countries are essentially what you might call the developed countries. And this is the developing countries. So you notice the contribution of the developing countries all together, which is about 1/8 of the developed countries, okay, is roughly the same. Let's do it as a per capita. What you see here, the rest of the world per capita has contributed much, much less than the OECD countries. And these are the economies in transition. This is essentially Eastern Europe that essentially transitioned from demand to free countries, or somewhat free countries, depending on your point of view. Okay. Then you can also do a projection. The problem with projection is you need to know what people are going to do in the future. Incidentally, you can do the projection, and your whole goal is to prevent that projection being there, right? So there are two different, what you do is scenarios, and these are two different scenarios, RCP 2.6, which is roughly what Paris Agreement would lead to, and 8.5 is business as usual. This is roughly. So as you can see, depending on how you do this, even with all these projections, these two countries, these two regions are going to contribute a lot more. Of course, India is going to come up here quite a bit. If you go to RCP 8.5, and that's other Asia. So you can get a feel for how much people are contributing, are likely to contribute. So the bottom line is simple. Climate change is not just about greenhouse gases, even though we focus a lot on greenhouse gases. Aerosols also matter, and land use, land cover matters. And the climate impact of aerosols and greenhouse gases are not exactly the same, but this is just looking at a very simple way of simple approach. And don't ever forget the legacy, especially those of you who are going to inherit any money from your parents. Remember that. Okay? You got it from somebody else doing something for a long time. And the same thing with climate change. In the long run, with continued emissions, CO2 is going to dominate. There's nothing much you can do about it. Unless you stop emitting CO2 or take it out. But that's what aerosols do for climate. But there's the other phase of aerosols, which actually affects health. Okay? So let's look at the health impacts. When you breathe air, depending on the size of the particles, it goes to different parts of your lungs. Okay? Large particles, it stays in your nose and etc. If it's 2.5 to 10 microns, it gets to a certain part of the lungs. If it's even smaller, they go in. When you get to very small things, they literally get into the bloodstream, and then it can go to the brain and all sorts of stuff. This is a simplified version of the health impact, and this is from my colleagues John Wilkins and Jennifer Peel, which is 10 years ago. Essentially, if you think about it, when you inhale these particles, you can get cardiovascular issues, cerebral issues, and other issues. So it affects your health in multiple ways. I don't know much about it other than. Okay. Now let's look at what happened though. On the left, if you look at this, in America, for example, in 1985, this was the kind of picture you saw for aerosols, and this is California, and this is the eastern part. This is where they used to burn coal. And America cleaned up its act, mostly because of acid rain. And look at in 2015, this is so much better than this. There's a scale here, but you can't see. And it's in here. Okay. It's reduced by about a factor of 5. On the other hand, if you look at India, this is the Indo-Gangetic Plain, you can just see every day, most of the days. That's from the image, from the satellite image. So then you can calculate and ask yourself how much aerosol is over India. Ooh, the colors are horrible, sorry. The largest area you can see here is in the Indo-Gangetic Plain. This is called aerosol optical depth. That is, if you were to look from here out to space, how much light does it reduce? So aerosol optical depth of about 0.5 means it reduces it by 40%. Okay? Roughly. And you can see most of India is pretty polluted, except for North India. And then the other thing to remember is, even though we spend a lot of time talking about organic aerosols and all that, India has a lot of sulfate and nitrate. Okay? It's still burning coal that has a lot of sulfur in it. And dust is a significant part of India's contribution, but dust is not all natural. It's resuspended dust. And then there's other things that you can think about. And again, we divided India into 6 regions, depending on the development. and some other considerations, mostly meteorological considerations. And let me just tell you how the first thing we need to know. It's one thing to see how much aerosol is above us, but we live close to ground. So we want to know how much aerosol we are breathing. Okay? But unfortunately, in India, there are not enough stations measuring pollution. I mean, Bangalore actually I think has about 30 maybe. It's the population of 15 million people. Okay? And if I were to go to Fort Collins, which has a population of about 200,000, we have about 30 stations. Okay? So this is the kind of disparity you have. So we have to figure out how much. So the way we did it, and it's actually other people also have done it, is use the satellite to measure the aerosol optical density. Then also use these stations called Aeronet, which is a robotic system that looks up and gets information. And then there's the ground-based measurements wherever you can get it. Then you compute or measure the vertical profile of aerosols. And knowing this, I can use a computer and we use a specific model called GeoChem. It's a chemical transport model. And then calculate the surface PM 2.5. So yes, it's all going to be biased towards daytime because that's when the aerosols can see these things. And secondly, there are going to be some differences. The spatial resolution is huge for satellite. Okay. Something to remember. But when you go through this, we don't do so bad. This is, you can't see it at all. The reddish color is data from Vinayak Sinha and Barbel Sinha in Mohali for a specific day, specific date, and we may calculate it from our method what it looks like. It actually does pretty well. You don't expect to have day-to-day variations this way because it could be some concentration here and a different concentration like 2 kilometers away, even 1 kilometer away. Okay? So overall, we do pretty well. And then there's also a question of variability. Variability is not error. It just is that it's variable. Okay? So when you do this, then you can ask yourself, what do you see? So the Aeronet data is extremely useful. Those are the Aeronet stations on the left-hand side. And then the satellite-derived information is in the vertical here. Okay. And then we can use India's available climate pollution, CPC, whatever that is, I forgot, measurements. And you can see overall the agreement is pretty good. Okay. It correlates quite well. And with the Aeronet stations, which is fewer in number, again, it's pretty good. Now, I'm not suggesting that it is good, better than maybe 50% accuracy, but that's what we got. And then I can calculate and ask myself, what is the level of this pollution across India? Okay? And unfortunately, I don't know. Anyway, you can see, I wish you could see the colors. The colors are really exaggerated because it goes up to 200 micrograms per cubic meter. Okay? And the thing that you see, of course, is the Indo-Gangetic plain sticks out like a sore thumb. It's very polluted. But there are other regions too. And the fact is, even if it is 50 micrograms per cubic meter, which you can hardly see on this picture here, it really is still bad. It's well above the health limits. Okay. The only time when India cleans itself up quite well is June, July, and August. Can you guess why? It's the monsoon season. Okay. So, then we calculated what is the health impact of this. Now, there are some uncertainties and errors in this calculation. Because the epidemiological studies have not been done for India per se. So we are using what's been done for other countries with much less pollution. But if you use that, you calculate some numbers. The way you do this is essentially you calculate the risk of people dying, and then look at the statistics of how many people died in different regions, and then multiply the two, and you can figure out how many deaths you can attribute to pollution. So overall, we come up with a number of about 1.4 million people per year dying because of air pollution. It could be off by a factor of 2. Okay. Now, I know it's very callous of me to say that, okay, whether it's 700,000 or 1.4 million, that's a lot of people. Okay. So if you were to put pictures of all the people, then you'll see what it means, how many people there are. Okay, so this is reasonably agreement with what others have done, but again, I want to tell you that unfortunately we don't have very good epidemiological studies in India. I lived in a village for 10 years, so I've never forgotten the village issue. So the thing that I wanted to do, or look at that, at least we wanted to do, was how does the pollution vary between urban and non-urban regions? People always think of pollution as cities, polluted cities. In fact, in North America and Europe, it's synonymous. This air pollution is an urban problem. So the way we did this is first we looked at the night sky data, and you can see the light, which indicates where the cities are and how much. You can actually quantify this. Okay. There's Chennai, there's Bangalore, there's Hyderabad, this is Pune, this is Delhi, Mumbai, Ahmedabad, Delhi. Now I forgot some other place. Anyway, but you see that you think there is not much here. But if you look at the census data and what is the number of people per square kilometers, there's a lot of people here, away from the city. And there's a lot of pollution there. The same thing is true in South India too. So, if you then calculate what does it look like, this is what you see. This is the population in millions as to what they're exposed to in pollution. Okay. The thing that you see, first of all, is bimodal. This second mode is almost all due to Indo-Gangetic plains. But this is the India's air quality standard. This is the World Health Organization's air quality standard. Okay. First of all, even India's ambient air quality standards, most of the people, they're not meeting it. Right? And then if you think about the World Health Organization standard, 0, zilch. So everybody is being exposed to this pollution, not just the people in the cities, also the people in non-urban areas. If you want to know why I call it non-urban versus urban, we can talk about it afterwards. Okay, we can just do this a little bit more and do it as various kinds of plots. So what I show here is the annual mortality per million. This is the urban, this is the non-urban from all the different regions. The double whammy of the Indo-Gangetic plain, this is polluted and it has a lot of people. So a lot of people are being exposed to a lot of pollution. But it doesn't go down all that much. And the reason is the exposure response curves are not linear. It's logarithmic. So if you reduce by a factor of 2, you don't gain that much. Okay. India's air pollution is so bad, you have to reduce it by about a factor of 10 before you can get somewhere. So I can show this in a different way. There's the urban on the left-hand side, annual mortality in millions, non-urban on the right-hand side. Then you look at the populations, India is still pretty much a non-urban country. There's a lot more people outside the cities than in the cities. It has changed in my lifetime, but then if you calculate mortality per million, as you can see, they're almost the same. But don't think the non-urban air pollution is all because of something coming from the urban regions. There's a lot of bad emissions in villages and stuff like that. A lot of it, if you could see those colors, which I'm sorry you can't see, is due to residential burning. There's a lot of stuff. That actually has a simple solution, if you think about it. If you were to give them something other than wood burning, you would reduce it by a factor. I just want to tell you that we have seen this movie before. This has happened before. I don't know if any of you can see or even can any of you guess where these pictures are? I'm sure if you can look carefully enough, you can see this picture. This is Delhi, right? Okay. And this, Paris. Okay, what about this? Huh? And this, let's see. This is the Statue of Liberty. Good. Now let's figure out when that was. Okay, that is America in 1948, London in 1952, Delhi, it could be any day, Paris in 2014, and this last one is last month in New York City. Okay, so the key point is, we know air pollution, this thing is not new. We know what to do to clean it up. It's been done before. Secondly, local knowledge of where the emissions coming from are critical. So India needs to develop its own emission inventory. Air quality is still a problem in undeveloped countries, and it's also getting to be a problem again. So the key message I want to tell you is air quality is not a problem that you solve. It's a problem you live with and you manage. Okay? It's like there's no simple cure. The only way you can improve the air quality is to take all the humans away from Earth. And then there's no point for humans to worry about it, right? Is there? Okay. So, let me just kind of drive this home by a simple point. The climate story I told you, India and China and developing countries actually haven't contributed as much as they would have, but they have. Look at the health impacts on the other side. India's health impact is about, because of the aerosol, essentially it's about 2.5 times that of the US. So the other way of saying is, Indians are paying with their health for better climate. So, I can talk until cows come home about climate change, but the thing that's choking India, literally, is pollution. Okay. This is all well and good. What can we do about it? So the thing that we did was take up the opportunity of COVID. What did COVID do? It really affected your lives, didn't it? You all were stuck at home, and you couldn't go anywhere, at least sometimes. And it also meant you actually reduced certain activities. Okay? So let's look at what that tells us. So if I were to look at the emissions, the concentrations and emissions of NOx, it really in America, it really went down quite a bit. CO2, not so much. Methane, not so much. I mean, this is expanded scale. It's starting at 300. Let's look at CO2 for the long term. It's going from 1960 to 2023. I don't see any COVID effect. So let me blow it up and look at this. No COVID effect. So during this time, as much as we say that the world almost came to a standstill, we're still putting out the same amount of CO2. Didn't go down all the time. You can see the NO2 change from the satellite picture. It did reduce emissions, but the question is how much and from where. So, why do we worry about something like COVID? It's simply because it's a perturbation experiment. And the way the perturbation that responds is shorter the lifetime, that means aerosol, quicker it goes away. Longer the lifetime, it doesn't change very much. So this is a simple way of doing it. And we did it with PM for two reasons. I'm interested in PM, and ozone is hard to do. Ozone has multiple emissions that can change, and the ozone production is not linear in the combination of the two. So let somebody like Sachin or Gulfam, who's watching, hopefully, do those kinds of hard stuff. I like to do simple things I can do. Okay, so this is a way of thinking about it. So let's kind of make it even clearer. So if I were to imagine what the emissions were during pre-COVID, during COVID, there was a lockdown, for example, and it should have gone down. And then it went away. Of course, it was not a square wave. You all know that. And also, when Chennai closed down, maybe some other part of India didn't close down. So it's not that simple. But anyway, we looked at some dates here, and remember there's a lot of variability, meteorology changes, and there's not well-defined COVID period, especially between countries. Okay. China shut down, really clamped down, but North America was off and running pretty much for a very short. So we kind of looked at it both during the specific COVID lockdowns and for the years where there were lockdowns. So to do that, again, we did the same kind of stuff. There's one slight complication, and that is, could the vertical profile be changed, which it did, and we have a way of accounting for it. There's a satellite, which is a LiDAR looking down that measures the vertical profile, and you can calculate it and see how the change. So we corrected for the fact the vertical profile was different, slightly different. Then if you look at the signals, the thing that you can see is very clear. The vertical axis is the calculated amount. It goes from 0 to 400 here and 0 to 60 over there. I mean, the different scales. India has so much more pollution, I have to put it on a different scale. The thing that you notice is all these points out here, large concentrations, okay? And as soon as COVID was shut down, there was much less emission. It's still significant. It's like hundreds of ppm, hundreds of micrograms per cubic meter, but it was not as large as some of these here. And then post-COVID, it just came back up again, and so did in America. And you can do these things called box and whisker plots, where you calculate the median, mean, and 67%, 95%, etc. And those are the plots that are shown here. So you can look at the geoscam, satellite, and the monitored data. You can see, yes, there was a reduction during lockdown. Okay? And same thing for India. Now, this just doesn't show up. Sorry about that. It did reduce PM, but it was the post-COVID pollution was larger than in shutdown period in North America because there's wildfire smoke. That complicated the issue. India did not have wildfire smoke, and it came back for gangbusters, as you can see here, lockdown, post-COVID, it's just very obvious. Okay. So the slowdown and shutdowns did reduce PM 2.5, and which it should. It is not a surprise, it should. And how much did it reduce is the key question. Also, post-COVID pollution is larger than shutdown and pre-COVID because of some seasonal influence. If you had the shutdown during monsoon season, you won't have seen much change at all. So let's kind of think about that for a second. So even if you compare only the short-term reductions as opposed to, instead of the short-term reduction, what the annual amounts were, it's almost nothing. Because your shutdowns are only for a few months. Okay. Now, there's also an issue of did transport from other regions influence the PM 2.5? That's something to think about. But this actually tells me a key message from my perspective. Oh, let me just show you one more picture here. And incidentally, you can do the same thing for urban and non-urban, and you get the same idea. The thing that I want you to notice is, yes, during the shutdowns, they did decrease, okay? But notice that even with the decrease, except for Western India and possibly South India, it never met the Indian standard, pollution standard. Okay? And of course, the World Health Organization standard is way beyond. So, what did we learn from this? The first thing I'll tell you is that the reduction in PM sources indeed will decrease PM levels. So that's the good news. So you know what you need to reduce your pollution. You need to stop driving so much. You should, all those things are obvious. It actually COVID showed if you do it, you'll get the benefit. Okay? But it also told you how much you need to do. If you just, what the COVID did was reduce it by about a factor of 2. Now you just ask yourself, why is it only a factor of 2? Because we're all here post-COVID, aren't we? So we were all fed, we all had our food, transported, all the food was grown, all the things that people do were done. That takes energy. So there are a lot of emissions that continued like that. But it also tells you the bottom line is, can we live with as strict as a COVID shutdown, or even stricter, to reduce the air quality? In other words, for India to meet its health standards, you have to be even stricter in what you do than during COVID. That kind of gives you an idea of how much action is needed. Okay? That to me is the key message. But there are some other interesting things we can think about. But I want to end with, what do we need? Obviously, I told you, we need emission reduction. That's completely clear, and you can do it. But the other thing that we need is we really need many, many well-placed ground observation stations. And I would say that if India were to put up a couple of geostationary satellites to look at the PM 2.5 at a high resolution, you can actually do it almost by 2 kilometers or 2 kilometers, even better. That will be extremely helpful. But this thing is critical. We really need better epidemiological studies for Indian population. And as I told you that we're using something that may not be completely applicable. And in fact, COVID showed you that. Because from COVID, the way it affected other people is different than what affected in some other places. I personally would like to see something like a personal monitor. Just imagine a world, that's my grandnephew, I made him stand out there, with something that measures air pollution in that little doodah, right next to your mouth, very close to you. That will be your personal sensor that will tell you what you can measure. So since you are all at IIT and you have all these wonderful engineers and scientists, that's what you need to develop and do. Okay, let me just summarize what I've tried to tell you. So the first point is developed countries have contributed more to climate change than the developing countries. PM 2.5 in developed countries have reduced climate change, but at a cost to the bad health. And PM 2.5 have continued bad air quality is not a choice. And I found this in very many circles. We can talk about climate change to people. Right now, that's not what they're worried about. I actually did a study in Bangalore where we had these personal sensors on auto rickshaws and driving around. Okay, and I didn't have time to show all the data. I did, perfect. But the most interesting thing I found then was when I asked these people what is the worst thing, they weren't talking about pollution. They said the potholes and their back was killing them. Okay, so there are other bigger issues that people worry about. We shouldn't forget about. Legacy is an important issue, both for the future and the past. And to think about what way forward for countries like India, you need large reductions in emissions. That doesn't mean you can't use energy, just that you use cleaner energy. And that's the simple solution. And the reason that's actually a better way for India is India does not have the same level of grids and all those things that other countries have. It's a big opportunity. To me, always I think about how cell phones changed India. I know you guys probably don't remember, but when I was growing up, there was one phone on the end of a street. One phone. Okay? Now, all of you probably have a couple of cell phones. And you do everything with your cell phone, right? And the reason you could do that is because essentially the whole infrastructure was so old that, and that's why Americans don't use cell phones as well as Indians in developing countries. And coping with climate change may be harder than developing, harder for developing countries because there are some other issues that we can talk about. I didn't talk. With that, I thank you for your attention and I will stop. Did any of you understand it?
Yeah, a couple of questions, probably. You have?
Very interesting talk, Professor Ravi. So it's surprising to see the positive impact of PM 2.5 on the climate change and not the negative effect. So I was just wondering, like, you didn't touch upon the sources of this PM 2.5, and like, you look at the geographical disparity across India, and the Indo-Gangetic Plain being very, very, pretty bad in this sense. So what do you think is contributing? Is it the geographical barrier of Himalayas, or that's not really allowing it to escape, or because industrialization is evenly distributed? It's not like north is much more industrialized than south. The industrialization is pretty evenly distributed. So what exactly do you think is contributing to that?
There are a few different reasons for it. The flow along the Indo-Gangetic Plain is due to the meteorology. Okay? But the emissions are still much higher in the Indo-Gangetic Plain because there are a lot of emissions that you don't think about. There's still a lot of cooking using wood and all sorts of stuff like that, and other sources of pollution. And amazingly, a very large number of thermal power plants are in North India. It does not have as much. Karnataka, for example, has a lot more hydroelectric than But the other thing is, honestly, Karnataka gets its energy from Orissa or something. So that's where they have put up a lot of thermal power plants. That's one of the reasons. And the reason South India is so much cleaner is because of meteorology. In fact, Sri Lanka is almost completely, pretty clean. It's not that industrialization is less, but Sri Lanka has the weather, and Bangalore is much cleaner than most other places because it's higher up and it gets blown away. You're going somewhere else. If you could see the pictures better, I could have shown you where it goes. I have no idea if you can see it. I'll show you afterwards on my computer.
Great, thank you. Appreciate your talk. It's an eye-opener, like the other speaker, the person just mentioned. We usually look at PM 2.5 or ultrafine particles, which we didn't talk much, as a menace, and now we are seeing the other part. Now, in your equation, especially with that radiative force you mentioned, you took only the atmospheric, the particles in the air. But what about those things that are happening on the ocean? It may not be particles in the ocean, but maybe something that happens with the warming up of the earth. So, I would have assumed that there may be something to do with even.
My first answer would be that the temporal and spatial variability tell us that the aerosols are closer to emission regions than somewhere else. CO2 gets equally distributed across the globe, but PM 2.5 doesn't go that far out. Okay? Now, the other thing that I don't know if you're referring to that, the effect of PM 2.5 going into the ocean and changing the nutrient issue. Is that what you're thinking about?
Yeah,
There are lots of feedbacks you could think of. Yes. We just did simple calculations. But we can run the climate models and do it. I find climate models, don't get me wrong, I love them. But I don't get a physical feel for things. I would like to think in terms of simple physical picture that tells us. And that's why I kind of thought looking at total energy is a much better way of physically understanding what's happening. You can have so many other feedbacks we did not talk about. I don't think, incidentally, even though I told you this, I still don't think it's going to change the qualitative conclusion of what I told you. It's likely to change the quantitative conclusion.
I happened to see an interesting article about bringing down the CO2 level by the growth level. So what is the growth of RAVI? In fact, there was a company that was involved in seeing the CO2 dioxide.
Yes.
When you mentioned, it may not actually bring down CO2, is there an
Yes.
this kind of manipulation?
In fact, there are proposed stuff. That's what you call a negative emission. First, is the carbon capture and storage. And it's very hard to do carbon capture and storage once it's in the atmosphere. And I once calculated how long it takes for the atmosphere to go through all the combustion systems on Earth. It takes 10,000 years. Okay? Just remember that. But the thing that it can do is capture it close to the emission regions. And that's one possibility. But then the question still becomes, where do you keep it? The other thing that you can do a calculation is, if you take the fossil fuel from underground, burn it, and put it back in there, can the CO2 you put back in, would it fit within that thing? It actually misses by about a factor of 2.5. It's simply because CO2 is 48 and hydrocarbons are pretty much like 14, for carbon. So there is that issue, and then of course there's the question of permeation. And the other thing that happens, as you probably know, if you put CO2 at very high pressures into those things, that's a supercritical fluid, it will start dissolving things and doing, there are lots of wonderful things to think about. Yes, personally, I have a philosophical and ethical problem. Who is going to determine how much temperature change we should do in the atmosphere in the world? So that's a good question. Thank you. One more question.
Sir, so you were saying that India needs a better emission inventory. So what do you think, having more ground stations is better, or having satellite measurements are better for establishing such robust emission inventories?
Both. If you have ground stations, are you an atmospheric scientist?
Yeah.
You could do like inverse modeling and get at emissions. And it's a little bit difficult with satellites, but you can still do it. Right now, people have been pretty successful trying to calculate methane emissions from satellites. But methane has a large background, so the aerosols will be much easier in that sense. So we actually did back calculate the kind of emission sources, and unfortunately, I showed you one, but you can't see it, the colors. Yeah, the ground stations will help you get the it's a simple source receptor. So if you can do inverse modeling to get at the sources. I think the guys who are on there, they're doing that kind of stuff. Ask them. We asked Sachin and Gulfam Beg and Tripathi and all those guys who are supposedly on the meeting there somewhere.
I was just wondering, how does one calculate the lifetime? Is it because of some model?
Yes, that's a very good question. I didn't actually tell you what a lifetime means.
No. Yeah.
Okay. You all know what lifetime means, right? But that's a very simple-minded thing. Lifetime is essentially the time from our birth to death. Okay? That's a lifetime, except if you have a distribution. And it actually is not a simple distribution for humans, incidentally. Have you ever wondered why there is nobody who's 150 years old who's living? Because we have 8 billion people. That's a good should have been a probability, but it doesn't. But I'm digressing. In atmospheric science, we define lifetime by saying, if I were to inject a pulse and watch as it goes down, time it takes for it to go down to 1/e of its initial concentration. Okay. But that's actually good if that decays like a first order. CO2 doesn't. CO2, that's why I was glossed over. CO2 is the first 50% of CO2 you put in the atmosphere within 1 year is taken by the biosphere. Okay. And then it goes down the ocean uptake, and then finally the way CO2 goes away becomes calcium carbonate and sinks to the bottom of the ocean. Yeah. So to answer your question, how do we determine it is, that's why I didn't like CO2. The ones that I can deal with as a chemist, I could study exactly how fast they react, and then I could calculate the lifetime. And that's what I did with methane. In those days, I could do one experiment and calculate and publish it in Nature. You can't do that anymore. Okay.
Okay. For the one, you have a question? Quick, last one. Okay. We have an appointment
Also,
with the director.
So for those of you who want to know about radiative forcing, you can stay and I'll show you.
Hello, sir. Sir, if you look at the socio-economic structure of India, you can definitely cannot eradicate all the sources of PM 2.5 or whatever, PM 2.5 or lesser. But if you are able to think.
Could you take over the microphone? Yeah, just speak. I can't hear you. So, yes, people have done very strange things. There was a guy in Bangalore who put these little towers to suck up PM 2.5. Okay, but you know, you can do that, but you can also do a very simple calculation: how much energy you need for calculating, reconnecting. Then you have to ask yourself how much pollution goes up somewhere else. So, if you do that, you'll realize that it's much easier not to emit it than to recapture it. These are simple calculations you can do on a piece of paper. I was going to tell them somebody who wants to stay. They want to know about ready to force. You really want to? I don't know. Rest of them want to go there. Things to do.
Thank you, Ravi. I request the department to give a memento. Yeah, you can open, but okay.
First act already, there is a, maybe I think Gagan circle, is it?
Yeah, no. Yeah, Gajendra Circle with
Oh, I'm supposed to.
yeah.
Thank you. Thank you.
You can open and see that.
So we can open it?
Yeah, we can open.
It's okay.
No, we can, yeah.
They have packed it.
No, we can take it out with your permission. It is.
You should see what you're giving me. And also, sir, at the security, I need to know what's in it.
Security. Correct.
Today you are leaving that.
Yeah, in a few minutes.
We are going to see the
So that I think we can tell you. If you tell it.
What is this?
Sorry for the last one. No, they are not from our research. Yeah, you can have a picture with them too. Yeah, that's fine. Straight. It should be that side.
essentially sunlight comes in and it warms the earth. And the earth then radiates energy according to Stefan Boltzmann, sigma T to the 4. So larger the more energy it has, shorter the wavelength, and the larger the amount.